Hi class. In this quick lecture, we're going to just learn some new vocabulary. So, first piece of vocabulary is that of empirical probability. So, what is empirical probability? It's computing probability from data. Well, to see what that means, let's look at an example. Suppose you want to figure out the probability of having red hair in the United States. So the probability that a random person from the United States has red hair. Well, asking every one of the 300 million people what color their hair is would be a lot of work. So instead, you select 100. 100 random people. And you see what color their hair is. From these 100, you see 5 have red hair. Red hair. And 95 do not. So what all that empirical probability means is that you look at our random sample and you use the probability in that sample and just assume it'll apply to everything else. So then we have the probability of red hair equals 5 divided by 100, and this equals 0.05. So we say the empirical probability of having red hair based on this data is 5%. Now, maybe the actual probability, so actual probability could be different. Could be different. But that's what makes this an empirical probability. We have incomplete information, and so that's the best value we can come up with. Right? Another example might be that we have a giant vat of marbles, and let's say we want to know the probability that a random marble is blue from this giant vat of untold millions. Well, we randomly select 50 and observe the color. And this is what we see. We see that there are 15 red marbles. Let's say there are 20 blue marbles, and for green, there are 15. All right. So then the probability of a marble, being blue empirically is 20 divided by 50. Right? The denominator is just the total sample size that we have. So this equals 2/5. 0.4. Of course, in the giant vat of marbles, there might be the exact probability might be slightly different, but from the data we've seen so far, that's the empirical probability. 9. Okay. Now the next concept is slightly different and applies to binary testing, really medical tests. So binary testing, e.g. medical tests, and what makes it a binary test is that it's either positive or negative. Right? There's just these two outcomes. And we've talked about used medical tests as examples in the past, and the things we've tried to answer about these is, for example, given a positive test result, what's the probability you actually have the condition? And what we've needed to know is, like, the false positive rate, false negative rate, etc. So these are just two terms that make encapsulating that information easier and communicating it faster. So what we want to the terms are specificity of the test, and sensitivity. Right. Sensitivity. So let's talk about first about specificity. Specificity is the probability that a true negative, so somebody who doesn't have the condition, if it's a medical test, so true negative tests negative. So is the probability that somebody who doesn't have it gets a negative test result. And the sensitivity is the flip of that. So it's the probability that a true positive, so somebody who has the condition, actually tests positive. All right, so in terms of specificity and sensitivity, let's do a quick, let's answer a quick question. So how do we express false, positive, false, negative rates in terms of specificity and sensitivity? Well, let's look at false positive first. There we go. False positive. So false positive is a true negative that tests positive. So it's kind of the converse of specificity, which is a true negative testing negative. So for the false positive probability is 1 minus the specificity. Since a person either tests positive or tests negative, there's no other options. And then the false negative is a true positive who tests negative. So that's the opposite of sensitivity, which is a true positive that tests positive. So this is going to be 1 minus sensitivity. Alright, so let's do a quick example. So a test, let's say for Lyme's disease, has specificity of let's say 98% and a sensitivity of 95%. Now let's suppose 10%, or that's 1%, 10% of the population has limes, right? Then the question is, what's the probability that if you test negative, you don't have it? Alright, let's begin by making a tree. So I'll make it from left to right. So we either have it or you don't. Let's call that L for having Lyme's disease and L complement for not having Lyme's disease. And we said that 10% have it, so then we have 0.1 probability that this random person has it, and a 0.9 that they don't. So we have a specificity of 98, and that's about true negatives testing negative. So then if we have our true negatives, which is our L complement, we're saying that 0.98 will test negative. I'll do test negative, and well, the complement of that, 0.02, will test positive. And now, for our true positives that have Lyme's disease, we have a sensitivity of 95%. So 0.95 will test positive, and 0.05 will test negative. So then the probability that a person who tests negative doesn't have it, so this is the probability of being a true negative, so being an L complement, given that you test negative. Alright, so this is just another conditional probability calculation. It's the probability of testing negative and being a true negative divided by the probability of testing negative. Alright, so from here on out, you've seen many examples of this. You can finish this example on your own. Alright. Alright, hi again class. So for this part of the, for this half of the video, I'm going to be going through the brief assignment that you have to try to digitally upload by the end of day, Friday. Alright, so it's not particularly important that you put your name on, but because I'll know who's uploading what, but I'll just write my name there. Alright, so let's look at the first question. If you're creating a general screening test for a rare disease, is it more important to have high specificity or high sensitivity? Well, I guess when you're asking about what's important, it's what are we trying to achieve, in this case, minimize. If you have a rare disease, the danger of conducting a general screening is that you have way more false positives than true positives, simply because the true positive population is so small. So what we want to do is to minimize false positives. Alright. And how are false positives related to specificity or sensitivity? Well, if we recall from before, false positives equals false positive rate, right, is 1 minus the specificity. So if we want the false positives to be low, then we want the specificity to be high. And by high, of course, we mean close to 1. It's the highest a probability could ever be is 1. Right, so to minimize false positives, want high specificity. Okay, let's look at the next question. If we are making a test for a highly prevalent disease, should we try to get very high specificity or sensitivity? Well, the danger, right, if you're screening for a highly prevalent disease, is that you might not catch everyone. So what we would be afraid of in this case might be false negatives. So to minimize false negatives, let's see, how are false negatives related to specificity or sensitivity? Well, as we covered just a little while ago, the false negative rate is 1 minus the sensitivity. Sensitivity. So to minimize false negatives, want high sensitivity, close to 1. That's that. I just wanted to go over some of the sort of practical meaning behind specificity and sensitivity. Alright, so the last and final question. So a new test for COVID-19 is studied. So this is actually data I looked up the other day on what kind of tests they were using that are in such short supply. This is a rapid test, and to figure out how good it was, they took 100 patients with the virus, and 99 tested positive. 1 tested negative. They took 100 known healthy patients, and 73 tested negative and 27 tested positives. So we'll use empirical probabilities to calculate the probability that a random person who tests positive has the disease, given that 1% of the population actually has it. Of course, that 1% is completely made up by me. It's the actual percentage is changing every hour, and by the time you read this, it might actually be 1%. Who knows? All right, so the empirical probabilities tell us that so of these 100 people, we had 100 people with the virus, true positives. We had 99 test positive, 1 test negative. So this says that, according to this limited data, that the sensitivity equals 0.99. So it's a very sensitive test. If you have it, you're going to be tested positive most likely. Likewise, the specificity equals 0.73. That's the empirical probability. So this is not a very specific test, which means that if we were to just test everyone, we would have a huge number of false positives. Now, assuming 1% has it, let's see how this goes. So we have a person here, they either have it or they don't. So let's say C for having COVID-19, C not for not having it. And then, so we have 0.01, 0.99, And of those that do have it, they're almost certainly 0.99, this is the sensitivity, going to be tested positive, so test positive. And only 0.01 are going to test negative. Of those that don't have it, well, the specificity is 0.73, so we only 0.73 are going to test negative, and 0.27 will test positive. That's the probability of testing positive is 0.27, given that you don't have it. Alright, so now what we want to do is the probability that that's what we're doing. The probability that our person who tests positive has a disease. So we want the probability of having COVID-19 given that they tested positive. That's the familiar formula. This is the probability of having COVID-19 and testing positive divided by the probability of testing positive to begin with. Alright, so we can plug in the numbers here. This equals, well, there's only one path that's having COVID-19 and testing positive. That's this guy here. So this is 0.01 times 0.99 divided by the probability of testing positive. So we have two paths for testing positive. We could this path or this path. So the first one is what we just did, 0.01 times 0.99. That's having it and testing positive, plus not having it, 0.99, and testing positive still, 0.27. Right. Plug this into a calculator, what you get is 0.0357. Roughly 3.5%. So if one were to apply this test, and there's obviously other tests, this isn't the only one that people use, but if one were just to blanket apply this to everyone, only 3% of the people who test positive would actually have the disease, and that's not well, it's 3 times greater, but it's not that much bigger than the number that actually have it to begin with, so a bigger of a percentage. So what this means is that actually just blanket testing people, if this is the test available, wouldn't really help narrow down who has it and who doesn't have it, because you just have such a huge group of people who test positive, and only a tiny fraction of them would actually have the disease. Of course, there's many reasons why it's hard to get tested, and this isn't really one of them, but I thought it was an interesting little thought experiment. Alright, so for you guys, I want you to try to fill this out and upload it digitally, scan it with your phone, etc. By the end of Friday, and we'll see how this goes, if they're all legible, if anyone hits any snags. Hopefully this was easy enough to follow.